Hey folks, it's Miss Gray. Welcome to Chemistry. Today we're looking at podcast 5.6 and we're going to figure out how to sketch molecular structures for covalent compounds. You'll find this in chapter 8 in your textbook, so let's get right to it. The molecular compounds, remember, are those that are covalently bonded. So a molecule consists of a neutral group of atoms. None of them are charged particles. Well, some of them may be charged particles. A neutral group of atoms, though, means that all charges add up to 0. And they're joined together by covalent bonds. And then we talked about covalent bonding before, but let's review. The sharing of electrons between two or more atoms is what creates a covalent bond. Now remember, these may be polyatomic ions, or they may be simple atoms. So a molecular formula is used to describe what types of atoms are in the compound. We cannot use the crisscross method for determining the molecular formula of this type of compound. The crisscross method works really well for ionic compounds, but not so great for molecular structures. We can only determine these by creating a structural formula using the Lewis dots that we learned before. So I showed you how to do the dot diagrams for individual atoms and individual elements. Now we're going to use the Lewis dots to create structural formulas for an entire compound, kind of like we did in bonding basics. Remember, the octet rule means that atoms are going to get the configuration for noble gas by sharing electrons. So hydrogen tries to look like helium, everything else is going for the octet. So here's how we do a structural formula. We use a dash to show a bond and a dot to show unshared electrons. And one example we did before was hydrogen. See, hydrogen has each atom has one single electron, so when they share electrons, they get the configuration of helium, which is a noble gas. So we show the structural formula by using a dash to represent bonded electrons. So when we're drawing structural formulas, we're going to follow these 4 basic steps every single time. Step number 1 is to count the total number of valence electrons for the compound. Let's work with the example methane, CH4. Carbon has 4 electrons, 4 valence electrons, and there's 1 atom of carbon, so there's 4 valence electrons coming from carbon. Hydrogen each has 1 valence electron times 4 atoms of hydrogen, for 4 electrons coming from the hydrogen. Now we'll add them up for a total of 8 electrons. So we need to find a home for 8 electrons, and remember, every electron likes to have a partner. So we'll use those basic principles to draw molecular formulas. Second step is to arrange the atoms so that hydrogen is never in the middle, and the element with only 1 atom in the formula is usually in the middle, and it's usually written first in the formula. So again, we have methane, carbon's written first. We're going to put carbon in the middle and put hydrogens all around it. The third step is to fill in the electrons. Remember, we have 8 total electrons, starting around the central atom until all the valence electrons are used. So we have 8 electrons to fit in there. We'll put them north, south, east, and west so that every electron has a partner. How's that look? Pretty good, huh? Okay, next, draw lines or dashes for any shared electron pairs and leave all unshared electrons just right where they are. So here's our methane. We're going to draw a line to represent shared pairs of electrons. There you go. 4 single bonds there. Now let's try a few more. we've got water first. So our central atom can't be hydrogen, it has to be oxygen. Let's count up the total number of electrons. Oxygen has 6 valence electrons, and then each hydrogen brings 1, but there's 2 of them, right? So we have 8 total electrons to find a home for. I'm going to put in the electrons for oxygen in their places, and then the 2 from the hydrogen, I'm going to show as X's. They come right in, and so now I have 8 total electrons all paired up. Now I'm going to use a dash to represent a single bond anytime where we shared a pair of electrons, and then these electrons have to stay where they are. So there's the structural formula for water. Now let's try fluorine. Fluorine has 7 valence electrons. And which one should we put in the middle? Doesn't matter much because it's just F2, right? So I have 7 for each of my fluorines. That's 14 total electrons I need to show in this structure. I'm going to use X's for this one so we can see where they are. So they will be distinguishable from the first fluorine we had. So now look, every atom has 8 electrons and every electron has a partner. So we can simply show this structure with a bond or a dash for shared electrons, and then the unshared electrons have to stay where they are. So we give everybody their 8 electrons and show which ones are in the bond, and the dots represent the ones that are not in the bond. Okay, now the last one is ammonia. So let's see, nitrogen has 5 electrons. Then each hydrogen brings 1, so I have to find a place for 8 total electrons. I'm going to start by drawing the valence electrons for nitrogen. Then it's easy to see how hydrogen fits in here. How does it come to share electrons? And we get our 8 electrons just by putting our hydrogens right in. So now nitrogen has access to 8 electrons, and each of the hydrogen has access to 2 electrons. That's how we want it to be. So let's show this structure with lines or dashes to represent bonding pairs, and then dots for the non-bonding pairs. There we go, there's ammonia. So you've got a lot of electron dot diagrams to draw in your packet, so you better get to it. Remember, single bonds are formed when atoms share 2 electrons, or 1 pair. Sometimes, though, to satisfy the octet, we have to share 4 electrons so that everybody has access to how many they need. That would be 2 pairs of electrons, right? And then triple bonds are formed by sharing 6 total electrons or 3 pairs of electrons. That would be pretty rare because it takes a lot of energy to crowd electrons in that close. Because of that, double and triple bonds never form with hydrogen or with the halogens. Here's some examples of what a single bond would look like between hydrogen, then here's one between the oxygens, and then one between the nitrogens. And seeing these reminds me of something that you guys really need to know, and this is a good time. Some elements are called diatomic elements. Diatomic elements hang out in pairs. That's why it starts with di. They have pairs of atoms to form molecules. So in their elemental form, they exist with a partner. So hydrogen and oxygen and nitrogen, as they're shown here, this is the true elemental form of those molecules. They don't exist as individual atoms. There are 7 of these that you need to know, and I have a friend, Professor Dr. Brinkelhoff, that can help you remember them. See, if you can remember this name, Brinkelhoff, oops, I need an H, then you can remember which atoms are diatomic. It would be bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. And since there's 7 of them, if you look on the periodic table, they make a number 7 because you have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And then, stinking hydrogen's way over here, off on his own in La La Land, as usual. But at least this will help you remember which ones are the Brinkelhoff elements, because it's going to be really important that you know what these elements look like when they're in their pure elemental form. So when you're breathing in oxygen, you're actually breathing in 2 atoms of oxygen at a time for every single molecule. Double and triple bonds sometimes are needed to satisfy the octet for all of the atoms in the compound. So there's no other way to get an octet for nitrogen when there's only 2 nitrogens if we don't form triple bonds here. There are some exceptions to the octet rule, and I don't expect you to memorize these or to know them. I just wanted to point them out to you. They're on page 228, and so for small atoms like boron, it's such a tiny little atom that it can't really squeeze in 8 electrons around it. So if this is the valence diagram for boron, there's only 3 valence electrons. Then to form BF3, boron trifluoride, then we would simply need to bring in a partner for each of these electrons, and fluorine has to have its octet filled. And so we just fill it in like this. A partner for these electrons. Boron donates 3 to this group, and each fluorine donates 1, so that fluorine has the octet, but boron only has 6 electrons around it. And that's okay. Boron's kind of unique in that it can be stable with only 6 electrons because it's such a small atom. There are some other elements that can do this. Some atoms in the 3p block have access to d orbitals because it's in the 3rd energy level, right? And so sometimes they will be what's called hypervalent. In other words, they'll have more than the octet. They exceed the octet. Some examples would be phosphorus pentachloride and sulfur hexafluoride. So let's draw phosphorus with its 5 valence electrons. Do you see where the chlorines fit in? We'll put one of them here with its 7 valence electrons. And then we'll put one of them here. And so each lonely electron for phosphorus gets a chlorine. So there's phosphorus trichloride, but I want pentachloride. So what do? Well, we're just going to put a chlorine here, break up this pair from phosphorus and pair it up with a chlorine instead. And phosphorus can handle being hypervalent because it's got access to 3d orbitals. Being in the 3p block, it can fill in some of its electrons into 3d orbitals, so it can be hypervalent. And it would be a similar situation for sulfur, where normally our sulfur looks like this. We have 6 valence electrons. Well, guess where the fluorines are going to go? They're going to partner up with each of the 6 valence electrons and bring what they've got, their 7 valence electrons, into here. So what you'll notice is fluorine, chlorine, these guys are very, very reactive, right? And so if they're going to form a hypervalent compound, then it's usually going to be with highly reactive halogens like fluorine and chlorine because they're very electron loving. They like having all those extra electrons around. That's a pretty stable configuration for them. So now let's talk about molecular shape. It's important to understand that compounds are 3-dimensional, right? So we are doing the best that we can to draw them, but we can't draw 3-dimensional things on our paper. So I need you to know about VSEPR theory. It's the valence shell electron pair repulsion theory. This guides the shape of all molecules. Essentially, it says that the negative charges on electrons repel each other, creating molecular shapes where electrons get as far away from each other as possible. That's no surprise, right? That's the reason they lower their energy in DNF orbitals. So here's a common shape. The tetrahedral is arranged in three-dimensional space so that we could take a structure like this, where we would imagine it to be like 90 degrees here, but in three-dimensional space, if we bend it around a little bit more, we actually get 109.5 degrees in between our electrons. So that is quite a bit more space than just 90 degrees, right? So suppose that we had a structure where this piece wasn't there, where there were only three, and then there was a non-bonding pair here instead. Then what would happen is that these non-bonding electrons would smush the bonding pairs down out of the way. So you would only get 107 degrees instead of 109.5. A compound that does this is ammonia. So we would have ammonia with its 1 nitrogen and 3 hydrogens that form the trigonal pyramidal type of shape, so that the electrons are as far away from each other as possible. All right, now let's say that in this compound, one of these went away and got replaced by electrons. Then those non-bonding pairs of electrons would push the bonding pairs even farther out of the way. So now this bond angle, rather than being 109 or 107, is actually down to about 105. This is a bent molecule, and this is kind of like how water does. So we squish the bonding pairs out of the way to make room for the non-bonding pairs. Okay, let's take another one away. So suppose that this guy wasn't there anymore, and now all we have is a linear substance. So suppose we have like hydrogen fluoride. Fluorine has 7 valence electrons, and then hydrogen has only 1, right? So I'm going to draw that in here, and then that would create a shape where we have only 1 shared pair and then 3 non-bonding pairs. That would create a linear structure. You could also have a linear structure by having like double bonds. For instance, carbon dioxide has this sort of shape where there's double bonds, and that locks it in to sort of a linear shape. And of course there's other shapes that there could be. One I want you to know about in particular is the, not pyramidal planar, trigonal planar. Typo. The trigonal planar bond would be kind of like this one that we called trigonal pyramidal, except there's no unbonded pairs. So no lone pairs, we call it. No lone pairs to squish things out of the way. So you have to look and see how many electrons are there, how many bonds are there, and how many lone pairs of electrons are left behind. And that will help you to determine what shape that molecule will be. And shape determines a lot of things about the properties. So that's it for covalent compounds. I could see you guys in class, so y'all have a nice day. See you next time.